Hello and welcome to our lesson on understanding functions through function machines. In this lesson, we will revisit the analogy of functions as machines to solidify your understanding. We will then move on to the main part of the lesson, exploring what a function machine is and how it works step by step. After grasping the basic idea of function machines, we will run through some practical examples to apply this new knowledge. Let's get started with today's lesson. Function machines help us visualize and comprehend the step-by-step processes that functions perform on inputs to produce outputs. They break a function into its individual steps, showing exactly what actions happen to the input to produce the output. For instance, if we have a function machine representing f of x equals 2x plus 4, it would look like this. We first draw the input box, which tells us what we put into the machine. The two arrows tell us what operations are happening to the input. Finally, we get the output, or the answer, at the end. So here we can easily see how an input is doubled, then has 4 added to it, resulting in an output. If we wanted to know what f of 4 was, we can feed it into the machine. 4 is out input, we then multiply it by 2, getting 8, and add 4 to it. Our output is 12. This visual and methodical approach helps clarify how different functions operate, making it easier to solve and understand certain algebraic problems. When breaking down a term into its function machine parts, remember the BIDMAS rule: brackets, indices, division, and multiplication, addition, and subtraction. For instance, if we have a more complex expression like f of x equals 3x plus 2 minus 5, we have brackets, which involve addition, multiplication, and subtraction. Look for brackets first, so we start with x plus 2. After the brackets, we then multiply by 3. Finally, subtract 5. We can chain these steps together in our function machine. Input is x. Our next stage is a plus 2 because this is in the brackets, and then times 3 and minus 5. Therefore, once x has been through our machine, we get an output of 3x plus 2 minus 5. Now we're going to move on to finding inverse operations using function machines. To reverse or undo a function, we simply reverse the chain of operations in the function machine. This helps us find the inverse function. Let's take the simple example, f of x equals x plus 4. Here we input x, we add 4, and we get our output. Let's find the reverse. The original function adds 4. To undo it, we should subtract 4. So the inverse function, denoted f inverse of x, has an output of x, an inverse operation of minus 4, and an input of x minus 4. Let's now look at a more complex example like f of x equals 2x plus 3. The original function first multiplies by 2, then adds 3. To reverse this, first subtract 3, then divide by 2. So for f inverse of x, our output is x. We minus 3 and divide by 2. Let's see how we can use this understanding to solve equations. Suppose we want to solve f of x equals 2x plus 3 for when the output is 11. We can set up an inverse function machine by reversing the steps. In our inverse function machine, we first subtract 3 and then divide by 2. This shows that our inverse function is x minus 3 over 2. We can input 11 into our inverse function machine to find x. First 11 minus 3 is 8, and next we do 8 divided by 2 to get 4. Hence, x is 4. Alternatively, we could have also solved this by rearranging the equation. First, set up the equation to get 2x plus 3 equals 11. Rearrange by first subtracting 3 from both sides to get 2x equals 8. Then divide by 2, which gives us x equals 4. This rearrangement mirrors the steps in our inverse function machine. It is important to note that function machine analogies are not always appropriate and should mainly be employed when you have a simple function to deal with, involving only the basic operations of addition, subtraction, multiplication, and division. Another detail is that not all functions actually have inverses. A simple example of this is the function f of x equals x squared. If I tell you that x squared equals 4, would you be able to tell me a single value for x? No, because both of x equals 2 and x equals minus 2 are solutions to that equation. Therefore, f inverse of x, or 4, does not exist. This also applies to any quadratic function by the same logic, since the quadratic formula gives 2 roots. We will learn more about quadratic functions in a later lesson. By breaking down, reversing, and combining steps, we've equipped ourselves with a robust method for understanding and solving functions. Let's now explore further and apply this to more complex problems in our follow-up examples and exercises. Consider the function machine for the function f of x equals 3x minus 5. What is the output when x equals 2? Let's work this out step by step. Our input is x equals 2. Next, we multiply the input by 3. This gives us 3 times 2, which equals 6. After this, we subtract 5 from the result. 6 minus 5 equals 1. Therefore, the output of f of 2 is 1. Now let's look at a function composition example where we have two function machines working together. Suppose we have h of x equals 2x plus 3 and k of x equals x minus 4. We want to find the output of k of h of 2. Let's start by looking at the first function, h. Start with x equals 2 as our input. Then multiply by 2. 2 times 2 equals 4. Now add 3. So 4 plus 3 equals 7. The output of h of 2 is 7. Now we need to turn to our second function, k. Use the output from h as the input of k. This is 7. Then subtract 4. 7 minus 4 equals 3. Therefore, the output of k of 7 equals 3. So the output of k of h of 2 is 3. This shows how function machines can be chained together to create more complex processes. Finally, let's explore the inverse function. Consider the function f of x equals x plus 7. We want to find the input that gives an output of 10. First, let's draw out our function machine. We are given the output is 10. To find the input, we reverse the function's operation. Since the function adds 7 to the input, we subtract 7 from the output. So 10 minus 7 equals x. Therefore, the input that results in an output of 10 is 3. This demonstrates how using function machines can also help us understand inverse functions by reversing the steps. By working through these examples, you can see how function machines offer a clear and methodical way to understand and solve problems involving functions. In today's lesson, we explored the concept of functions using function machines to deepen our understanding of algebra. We began by reinforcing the analogy of functions as processes that take an input, perform specific operations, and produce an output. We then introduced function machines as diagrams that visually represent the step-by-step actions performed by a function. We demonstrated how function machines can show the process of adding a constant. We also emphasized the importance of following the BIDMAS rule when dealing with more complex functions. Next, we discussed finding inverse operations using function machines. By reversing the sequence of operations, we showed how to determine the inverse function, which undoes the original function's actions. Finally, we applied these techniques to solve equations by rearranging the steps in the function machine in reverse order. This approach allowed us to find the original input value given an output. Watch the rest of the GCSE Maths course at Sophos Education.